Hello, good afternoon, everyone. Thank you for joining us to another seminar of the Astronomy Department of IAG. Today, we have the pleasure of having Professor Gustavo Romero with us. We thank Gustavo for accepting the invitation to be here talking today with us. Gustavo is full professor of relativistic astrophysics at the University of La Plata and a superior research of CONICET in Argentina. Researcher, sorry. He's a former president of the Argentina Astronomical Society, and currently he's the director of the Instituto Argentino de Radioastronomía, ILIAR. He's one of the most frequently cited scientists of Argentina, and he has published more than 450 papers and 12 books. He worked in many institutions around the globe as visiting professor or researcher, and in fact, he also was a postdoc here at our institute. Most of his research is focused on black hole physics, gamma ray astrophysics, gravitation, cosmic rays, and ontological problems of space-time theories. He has received numerous awards in recognition for his work. And today, he is going to talk about the origin of mass in magnetized jets of blazars. And before we begin, I will ask, please, everyone to turn off your microphones and your cameras during the presentation. And if you have any question, you can indicate this in the chat, and the questions will be asked later. So, Gustavo, whenever you want, you can start it.
Okay, thank you very much, Maria, for the introduction. It is always a pleasure for me to come back to the IAG, even remotely like this. As you mentioned, I spent 2 years, a very long time ago, in the IAG, and I have very fond memories of the Institute and of the people in the Institute. Well, so today I'm going to talk about the origin of mass in the jets of relativistic jets of active galactic nuclei. And let me give some context for my talk before entering into the main topic. As you probably know, jets are collimated outflows of particles and fields. These jets are observed on many different scales, from galactic scales as in microquasars. These are some examples of the jets observed in microquasars. This is the case of the Cygnus X1, a very famous X-ray binary that contains a black hole of 14 solar masses. This is the first jet in the galaxy where a superluminal source was detected in 1994. This is the famous jet of SS433. It's famous because the jet is precessing, and you can see some signatures of this precession here in this radio image. And this is a jet source in the very close to the galactic center. And also, this type of jets appear in the so-called gamma ray bursts that are the result of the collapse of very mass stars or the fusion of two compact objects, for instance, a neutron star and a black hole, or two neutron stars. In the case of this gamma ray burst, the jets are extremely relativistic and can propagate on the interstellar medium along distances of the order of several parsecs. And then we have the extremely powerful jets of active galactic nuclei. These jets are powered by supermassive black holes with masses from 10 to the 7 up to more than 10 to the 9 solar masses. And these jets propagate first through the galaxy that contains the active galactic nucleus, and then through the intergalactic space. And they can reach sizes of the order of 1 megaparsec. Here you have some very famous examples. For instance, the jet in Cygnus A, a very famous radio galaxy. And this is the jet, the inner part of the jet in the famous quasar 3C273. This was the first quasar detected in 1963. And the famous jet in the galaxy M87. That is a very nearby galaxy with a well-collimated jet that is visible in radio here, in optical, and in X-rays. This is the very same galaxy whose supermassive black hole was imaged last year by the Event Horizon telescope. So essentially, all these sheds have some common features. All of them are very well collimated. All of them produce non-thermal radiation, and all of them have populations of relativistic particles that move along the flow. So the basic ingredients for the formation of these jets in all these different situations seems to be more or less the same. Essentially, you need a compact object, for instance, black hole, then accretion of matter with angular momentum on this black hole, and then you need magnetic fields plus rotation. And with these basic ingredients, jets seem to appear in a wide variety of circumstances in the universe. One thing that we have established about all these different types of jets is that the power of the jet is related to the accretion power of matter onto the compact object. This relation is called the jet-disk symbiosis and is expressed through this formula that you can see there. I have lost my cursor, I'm sorry. That reads the power of the jet is proportional to the accretion rate times the speed of light to the square. So in many systems, this constant Q is a number that is smaller than 1. For instance, in Cygnus X1, this microquasar that I showed you a moment ago, the value of this coupling constant is of the order of 10%, 0.1. So this means that about 10% of the accreting power goes into the jet. And this type of values are typical of jets in microquasars and also in some low luminosity jets in active galactic nuclei. But then we have some more powerful jets that are observed in AGNs and also in gamma ray bursts, where we found consistently that this parameter Q is larger than 1. This means that the energy is being extracted from the black hole, the rotating black hole. So the origin of the outflow seems to be associated with the accretion of large-scale magnetic fields onto the black hole. And these magnetic fields somehow extract energy from the rotation of the black hole itself. And this energy extraction can be so efficiently that the whole system can produce more power in the form of the jet than the accretion power of the system. So in order to understand how this is possible, I think this is a nice illustration developed by Tchaikovsky that illustrates how a compact object with a poloidal magnetic field can generate a magnetized outflow when rotation is included. In the first figure A, you see a sphere, let's say, that represents the black hole, and a magnetic field line that is attached to the sphere that is a poloidal magnetic field line. And the other extreme of the line is attached to some sailing. You can think about this sailing as, let's say, the gas very far away from the black hole. So as the sphere starts to rotate, then a toroidal component of the magnetic field develops. And as time goes by, this component starts to produce a magnetic pressure on the sailing. And when the toroidal component is much larger than the poloidal component, then the pressure of the field on the sailing is so high that this sailing can be pushed away. So at this point, we have a magnetic dominated outflow, where the velocity of the fluid is essentially the velocity of the field. And the structure of this outflow will be determined essentially by the structure of the magnetic field. Well, in the context of a black hole, this situation translates in the following. I will try to recover my cursor. Let's see if this works. No, unfortunately not. Okay, in the case of a black hole, we have a magnetic field that is supported by currents in the accretion flow. And this field essentially will have a strong poloidal component, but when this poloidal component penetrates in the ergosphere of the black hole, of the rotating black hole, then the poloidal component will necessarily develop a toroidal component. And so this will produce a twisting of the magnetic field lines along the rotation axis of the black hole. The result will be that power will be ejected in the form of a Poynting flux. And the value of this Poynting flux roughly can be calculated as you see here at the bottom. The luminosity, the electromagnetic luminosity of the outflow will be of the order of the product of the electric field times the magnetic field times the speed of light times the cross section that essentially is given by the square of the gravitational radius. So since the magnetic field is of the order of the electric field, then essentially the luminosity of the system will be proportional to the magnetic field to the square times c, the speed of light, times the gravitational radius to the square. So if we put some constants in this relation, what we get essentially is the luminosity given by the Blandford-Snijder mechanism. So in convenient units, this is for a magnetic field of the order of 10 to the 4 Gauss and a black hole mass of the order of 10 to the 9 solar masses, and a maximally rotating black hole of the order of 10 to the 46 erg per second. So you see that a huge amount of energy can be extracted by this kind of mechanism. So the main points of this magnetic mechanism for the production of outflows are the following. While the plasma is carried into the black hole only and never ejected, the electromagnetic power is what is ejected along the rotation axis. Then the Poynting power should be eventually somehow turned into particles at some point from the black hole. We know that this occurs because we can observe the radiation that are produced in these jets, and this radiation is produced by charged particles. So somehow the Poynting flux should be converted, at least partially, in relativistic particles. Then the magnetic field is tied to the unfolding plasma, not to the horizon. So always the currents that produce the magnetic field are in the accreting gas. The interior of the black hole, of course, is causally disconnected from the outer region. And the inner part of the accretion disk accumulates large scale magnetic field very close to the black hole. And this accumulation of magnetic field produces a magnetically arrested disk. This is a disk that in the innermost part is dominated by magnetic pressure. And this produces a series of changes in the structure of the disk that makes easier for the system to launch a jet. Then what twists the magnetic field lines and develops this toroidal component is the frame dragging in the ergosphere of the black hole. So in this mechanism, having a curved black hole is essential. Of course, you can twist the magnetic field lines if these lines are attached to the disk, as for instance in the so-called Blanford-Payne mechanism. But this mechanism cannot produce power as high as the case of the Blanford-Snag mechanism. So in this talk, I will focus on the Blanford-Snag mechanism and the jet that is launched from the ergosphere of the black hole. This will be a magnetically dominated jet. And then the back reaction of the magnetic field lines accelerates the plasma inside the ergosphere to relativistic speeds, but in the counter rotation, in the counter direction of the rotation of the black hole. So this plasma will get a negative energy, and it's the accretion of this negative energy plasma which decelerates the black hole. So the black hole will spin down, and is this energy that is transferred to the jet. And because of this, we can extract energy from the black hole, and we can have a jet with a power that is larger than the accretion power. Okay, so this situation is verified by a number of simulations that have been implemented in recent years, for instance, by Tchaikovsky, Narayan, McKinney, and others. Here you see simulation of the formation of a magnetically arrested disk. In the upper panels, you see the accretion disk, the formation of the accretion disk, and the evolution of the magnetic field. And you see that the magnetic pressure close to the black holes makes the disk quite thin close to the black hole. And this creates some channel in which the jet is confined. So the basic features of this magnetic model for the generation of jets are the following. First, relativistic jets are produced by rapidly rotating black holes that are fed by strongly magnetized accretion disks. The ultimate source of power in these systems is the rotational energy of the black hole, not the accretion disk itself. And this energy is extracted as a magnetic torque in the form of a Poynting flux. So at the beginning, the outflows is essentially a Poynting flux. The jet collimation is due to the external medium outside the mad zone. The mad zone is the magnetically arrested disk of the system. And then the acceleration of the jet is through the conversion of electromagnetic energy into bulk kinetic energy. So this presents a problem. This is the following. So the typically magnetic field in this disk are of the order of a few times 10 to the 5 Gauss close to the black hole. And with that magnetic field, the Larmor radius of a particle is given by this expression that you see here. And you see that the Larmor radius depends linearly with the Lorentz factor, and if you calculate for a magnetic field of few times 10 to the 5 Gauss, the Larmor radius, even of very relativistic particles, is quite small, much smaller than the typical size of the black hole or the ergosphere of the black hole. In the case of a supermassive black hole, as the one in M87, for instance, with a mass of a couple of times 10 to the 9 solar masses, this size, the size of the base of the jet is of the order of 10 to the 15 centimeters. So this is much larger than the Larmor radius, even of very energetic particles. So this essentially means that if a charged particles tries to penetrate inside the jet from outside, inside the outflow from outside, it will be rejected by the Lorentz force produced by the toroidal component of the field. So essentially, you cannot put charged particles inside from the surrounding plasma in your outflow. And this creates the following problem. What is the origin of the mass, of the initial mass in these jets? Because they start as a Poynting flux and they are shielded by the magnetic field. So what is the origin of the mass in these jets? And we know that there should be some mass in the form of charged particles, because we can resolve some of these jets. Again, this is on the left an image of M87, the base of the jet of M87. These are scales of the order of a few Schwarzschild radii from the black hole. And you see here synchrotron radiation, essentially. This is a map obtained with BLBI interferometry of M87, and what we are seeing here is infrared submillimeter radiation produced by relativistic electrons that are emitting in the magnetic field. So there should be some relativistic electrons in the outflow. So what is the origin of these electrons? What is the origin of these charged particles inside the jet? You see here that the shape of the jet is still a conic shed. So the shed is still opening. So it's not completely confined by the external medium. So we are looking at the very base of the jet, and we are seeing a lot of synchrotron radiation, and this means that we have many relativistic electrons in there. What is the origin of this relativistic electron? This is the topic of my talk. Well, if we want to answer that, we need to think in the context of the black hole and in the whole situation in which this magnetized outflow is produced. So this situation is sketched in the figure on the right side of the slide, where you see the black hole, the initially poloidal magnetic field lines, and you see the accretion disk. This is this magnetically arrested disk. And this disk is very hot plasma with temperatures that can reach 10 to the 9 Kelvin for the electrons and 10 to the 12 Kelvin for protons. And then we expect some relativistic particles in this flow. There will be some thermal relativistic particles in there, but also a non-thermal component might be present. And if that is the case, then gamma rays can be produced in this accretion inflow. And these gamma rays will penetrate in the jet, and they might annihilate inside the jet, the magnetically dominated jet. Electrons cannot penetrate protons cannot penetrate, but the gamma rays can do it because, of course, they are not charged, and they annihilate inside, and then they will create locally inside the base of the jet some electron-positron pairs. So we might ask how many of these pairs are created by this process. And if in the inflow, in the inner part of the accretion disk, we have also relativistic protons, then we might create some neutrons in the disk through interactions of protons with photons, or also through proton-proton interactions. And these neutrons also will be able to freely penetrate into the jet, and they will decay, some of them at least, in there. And when they decay, they will inject protons and also, of course, electrons and neutrinos that will escape. And also, even if the neutron do not decay inside the jet, but if it moves through the jet, it can produce some electron-positron pairs by interaction with photons. So I will explore these channels for introducing mass in the jet in the rest of my talk. Sorry? Control plus what? L. L. Okay, just one second. Let me see. Control L. No, nothing happened. No. Control L. No, I lost the cursor. Okay, well, I will try to figure out how to explain you all the things. Well, so I would then, if we are going to explore in a quantitative fashion this situation, we need to know a bit more about this magnetically arrested disk, the environment of the black hole. So, how is this environment of the black hole? At low accretion rates, the thin disk truncates at some distance from the black hole, and the innermost part of the inflow is filled by a very tenuous plasma, and this plasma can be very, very hot. It's essentially a collisionless plasma, so it will cool not efficiently. For this reason, the inner part is called a radiatively inefficient accretion flow, RIAF. It's a hot, inflated, optically thin plasma, as you can see in the figure. The hot electrons that are in this plasma, as I mentioned, with temperatures of the order of 10 to the 9 Kelvin, essentially will cool by inverse Compton upscattering of low energy photons that come from the outer thin accretion disk, and also they will cool through synchrotron radiation in the strong magnetic field that is inside this region. This synchrotron field will also be a seed photon field for additional Compton interactions. So cooling through by Comptonization of this synchrotron component might be important in this type of systems. So if this plasma, very hot plasma with two temperatures, is collisionless, it might also be quite far from thermal equilibrium, and at that state, some different type of mechanisms can contribute to accelerate a population of relativistic particles, non-thermal particles in this inflow. And the figure that is in the top part of the slide at the right, you see the spectral energy distribution that we have calculated for a black hole of 10 to the 9 solar masses with a radiatively inefficient accretion flow. The basic parameters for that calculation are in the table. So you see that the accretion rate is at the level of 10% of the Eddington luminosity. For the disk, the outer radius is around 100 Schwarzschild radii, and you see the other parameters that we have considered in the calculation of the thermal spectrum of this flow, hot flow on the black hole. And in the spectral energy distribution, you see at low energies a first peak. The peak is in the infrared, and this is the synchrotron radiation of the thermal electrons that have relativistic velocities. They are cooling in the magnetic field that has a value of the order of 10 to the 4 in this particular example, Gauss. And then the rest of the spectrum at higher energies is the result of Comptonization of different ambient photon fields, the field from the disk and also this synchrotron field that is produced by the relativistic electrons in the inflow. So you see that the emission from the RIAF goes up to energies that are beyond a few mega electron volts, so into the gamma ray domain. If in addition to this thermally originated radiation, we consider a population of relativistic particles in the accretion disk, then we will have additional sources of high energy photons. In order to estimate that, we assume that about 5% of the accretion power can go into non-thermal particles by some kind of mechanism. That might be, for instance, turbulent magnetic reconnection or turbulent acceleration in the flow. So we assume power law injection for these relativistic particles. We use a normalization of 5% of the accretion power, and then we solve for the different species the transport equation for these particles. So we have an equation as the one you see here in the slide for each species of particles. So these equations are coupled, and you have to solve all together. In this equation, B represent the different type of sources, the losses for the different type of particles in the source. Sorry. These losses include synchrotron radiation for electrons and protons, and also for muons, and the losses for electrons and muons also are inverse Compton losses, and we are taking into account proton-proton interactions and proton-photon interactions for hadrons. So in the spectral energy distribution that we are seeing here in this slide, we are plotting all these different radiative contributions for all particle species in the non-thermal part of the spectrum, and also we are including the thermal radiation. And we are calculating the opacity for the propagation of the high energy radiation. The opacity is due to photon-photon annihilation. And as you see, most of the radiation at high energies is suppressed by photon annihilation. So the final emerging spectrum of the RIAF is quite similar to the original one, what you are seeing at energies below a few MeV, but then you have a non-thermal tail that extends up to energies that are of several hundreds of GeV, giga-electron volts. All this is considering an efficiency for the acceleration of the order of 10 to the minus 3. Okay, so a lot of photons, of high energy photons, are produced in the innermost part of the disk. With this model, we can estimate how many gamma rays are you producing at each point of your disk. So you can calculate how many of these photons will be injected inside the magnetized jet. And then you can calculate what is the opacity inside the jet for the propagation of these gamma rays, and you can calculate how many electron-positron pairs will be injected inside the jet through the annihilation of these gamma rays. And this is illustrated in the plots that you see on the top left side of the slide. And from the first one, you see that the number of electron-positron pairs that are being injected per second per cubic centimeter is of the order of 10 to the 3, around 1,000. At in the region that is close to the black hole. This is the region that I call the base of the jet, the region where the Poynting flux is being generated. And if we think in essentially in power per unit of volume, then we have the second plot on the top, and here we see two peaks. One of these peaks is the result of the annihilation of TeV photons in the infrared field, and the other is due to the annihilation of GeV photon in the X-ray field of the produced by the accretion flow. So we have two peaks in the energy distribution of these pairs. So the total number of pairs that are being injected at any time in the base of the jet is very large. It's of the order of 10 to the 55. This means a production rate of the order of about 10 to the 48 pairs per second at the base of the jet. So this photon annihilation mechanism inside the base of the jet might be a very significant source of leptons, a mechanism for charging the jet with mass, as long as we have some efficient non-thermal acceleration process occurring in the inflow, in the accretion disk, in this inflated accretion disk. And then we have the neutrons that are also a source of mass for the base of the jet. And these neutrons can be produced by the collisions between protons, according to these reactions that you see here. Proton plus proton gives us proton plus neutron plus a charged pion plus the fireball, and also neutron plus two charged pions plus the fireball. And then also we have photopion production, and in this case proton plus photon gives us a neutron plus the charged pion and eventually a fireball. So these neutrons will propagate and they will decay on a time scale in the proper system of the neutron of the order of about 10 to the 3 seconds into a proton, an electron, and anti-neutrino. And if this decay occurs into the jet, we will have an additional source of matter in the jet. And if the proton just moves through the jet, then there will be some chance for the neutron of interacting with the gamma ray, with the photon, and producing a proton plus a pion inside the jet. And this yields an additional source of electrons or positrons when the pion decays. And protons also, the protons that are introduced in the jet through the decay of the neutrons will move at relativistic speeds in the outflow, the jet, and then they can produce more electron-positron pairs by Bethe-Heitler process. So this is the interaction proton plus photon gives you again a proton plus an electron-positron pair. And many pairs can be produced in this way by this process because the inelasticity is quite small. So in this figure that you see on the right side, you see the spectrum that is produced in the jet, at the base of the jet, by the spectrum, of neutrons that is produced at the base of the jet by these two different type of interactions, proton-proton and proton-photon interactions. So you see that photon-proton interactions produce neutrons with higher energies, and the low energy part of the spectrum is dominated by neutrons that are the result of proton-proton collisions. Okay. So now we can put everything together and we can calculate the total injection of electrons, positrons, and protons by all these mechanisms at the base of a magnetized jet. So this is what you are seeing here. In the first plot at the top, you see the rate of injection of electrons through the different mechanisms that I have been mentioning. Electrons that are injected by the decay of neutrons, by interaction of neutrons with photons, by Bethe-Heitler process, by secondary protons, by photon annihilations, photons that are from the thermal component of the disk, and photons that are from the non-thermal component in the disk. And you see that what dominates the injection of electron-positron pairs are these two later mechanisms, photon annihilation, both thermal and non-thermal. So this mechanism produce several orders of magnitude more pairs than all the other mechanisms combined. And the second plot in the same figure shows you what is the energy density injection in the base of the jet by the different mechanisms. And in the figure that is at the bottom of the slide, you see the injection of protons in the funnel of the jet, at the base of the jet. You see two different mechanisms. You see decay of neutrons in the funnel, and this will produce a proton, injected proton, and then those neutrons that are converted into protons by interaction with a photon. So the first mechanism is the dominant one. And in the second figure, you see the energy density injection at the base of the jet. So if we compare the injection of pairs and the injection of protons, we arrive to the following conclusions. First, that there are many more electron-proton pairs than protons at the base of the jet. So the ratio of electron-positron pairs to protons is 10 to the 5 in favor of the pairs. And if we think in terms of energy density, then the ratio of the energy density in pairs to the energy density in protons is of the order of 100 in favor of electron-positron pairs. So our conclusion is that the base of the jet can get some matter, charged particles, from all these processes, but the content of the jet will be dominated by electron-positron pairs, not by hadrons. And these are some additional plots that allow you to get some idea of what is going on at the base of the jet. This here we have the distance to the black hole in Schwarzschild radii as a function of the energy, and what we are plotting on in the figure on the left side is the injection of energy injection of protons, and on the right side the injection in electron-positron pairs. So you can see the distribution in energy of these particles. So for instance, the most energetic protons are injected very close to the black hole, and they have energies of between 10 to the 6 up to 10 to the 8 giga-electron volts, so very energetic protons indeed. And for the case of the electrons, also the most energetic electrons are very close to the base with energies that are above 1 TeV. And what happens with the magnetization of the jet? So the jet is expanding, the energy density of the magnetic field will decrease as the jet expands, and we are also injecting particles. And so we have estimated for different configurations of the jets that depend on the confinement of the jet and the prescription for the evolution of the magnetic field, how the magnetization evolves along the rotation axis of the system, that is the axis of the jet. So we are assuming here that the magnetic field changes with the distance to the black hole as a power law, and also that the radius of the jet evolves as a power law, and the index, this m and this b that appear in the expressions, well, depend on the specific configuration. It's not the same a conical jet than a jet, a parabolic jet, and other configurations. So we have considered a variety of possibilities. And for instance, in the case of a conical jet, the magnetization will decrease quite quickly. So at distances of the order of 100 Schwarzschild radii from the black hole, the jet will start to be dominated by matter, not anymore by the magnetic field. Okay. Now, if we want to have more matter in the jet, we need to consider additional mechanisms. And these mechanisms might be related with dynamical questions associated with the accretion of matter. One of the things that can entrain matter in the jet from outside is if the accretion disk produce some kind of wind. And this is very likely. There are simulations that show that there are winds that are produced by radiation pressure from the disk, and this wind has some trend to form clamps, and these clamps essentially from a macroscopic point of view are neutral matter. So in principle, if you have sufficiently dense clamps, it might enter into the jet. Now the problem is that if we are discussing what is going on at the base of the jet, then the magnetic field is so strong that the magnetic pressure will avoid this entrainment, unless that the density of the cloud is extremely high, densities larger than 10 to the minus 7 grams per cubic centimeter. And this is much larger than what we expect for clamps that are formed at the base of the jet. So this mechanism is not very likely to contribute to the matter content, at least at the base of the jet. And another possibility that is suggested by some simulations by McKinney and Blanford is that the jet might accrete, the accretion disk might accrete some non-dipolar magnetic field. And this non-dipolar magnetic field might result from some turbulence in the inner part of the jet. And this will produce some mixing between the turbulent outflow and the disk at the base of the jet. But that will result in a jet that many times might be disrupted. So this is not what we expect in the most powerful jets that propagate very collimated, in a very collimated way to very far distances. So summing up, this entrainment mechanisms are not very likely in the most powerful AGNs. So the injection of neutral particles, the locally creation of charged particles by neutral particles, at least in my opinion, remains as the main option for the charge of mass of the base of the jet. But of course, you can introduce mass in the jet far away from the black hole, in the region where the jet now is dominated by matter and not by the magnetic field. And this can be done in a variety of forms. For instance, if the black hole is surrounded by a region with clouds, the so-called broadline region, and where these clouds have velocities of the order of several thousand kilometers per second, then it is almost unavoidable that when the jet moves through this region, some clouds will interact with the jet, and the interaction of these clouds with the jet will result in the ablation of the clouds, and this will contribute significantly with mass to the jet, and also the increase of the mass of the jet will produce a deceleration of the jet. This has been studied by several authors, for instance, Anabela Araudo, Santiago de Palacio, and other people in my group have been working on this. And if you go even farther away, then the jet will escape from the galaxy, but when moving through the galaxy, the jet will interact with many stars. And these stars will have winds, and the interaction of the star with the wind will produce bow shocks, and these bow shocks will be a mean for the introduction of matter in the jet. And actually there are some observations in some nearby galaxies where we see stars inside the jet. For instance, here you have an image, a radio image, obtained with BLBI at 8.4 gigahertz of the jet in Centaurus A. Centaurus A is the nearest active galactic nuclei, and in this image you see that the jet has some kind of bifurcation. This is the result of the interaction with the star. So if you compare the location of this bifurcation that is pointed with the arrow with optical images, you will see that there is a star right there. So this has been interpreted as the interaction of the jet in Centaurus A with a star. And if we go to larger distances from the black hole, then and we look at the X-ray jet, you will see several spots that you can see in the figure that is on the right side of the slide. And these bright X-ray spots are interpreted as bulb shocks that are the result of the interaction of stars with the jet. And at each point, matter is being injected in the jet. Matter that comes from the wind in the stars, and also in the case of supergiant stars, for instance, this could be part of the, like in a red giant, part of the atmosphere of the star that is just skimmed from the star by the jet. All these mechanisms will produce a charge of the jet with mass, but all this will occur at large distances. If we are concerned just with the base of the jet, where rapid variability is produced, where many very energetic phenomena are produced, then we have many less options for the injection of mass. And everything seems to suggest that the jet will be dominated at these short distances essentially by electron-poston pairs. So the radiative mechanisms that will be dominating the radiation will be leptonic ones. So if we observe rapid variability in gamma rays, for instance, probably will be the result of inverse Compton upscattering of some photons there. So my conclusions are the following for the entire talk now. First, efficient relativistic jets start as collimated Poynting flux jets. So this is always the case when you have an efficiency that is larger than the accretion power onto the compact object. Of course, this is not the case when the jet is launched by other type of mechanisms, as for instance, the Blanford-Payne mechanism, or the kind of mechanism that operate, for instance, in galactic jets. Galactic jets as those, for instance, that are formed in Harvey-Harrow objects, or when the stars are formed. These jets are launched by the disk, and these are not relativistic jets. Then the initial matter loading of the jet will depend on the accretion regime. And in the case of that the accretion regime is a magnetically arrested disk that forms in a RIAF, the main source of particles might be the annihilation of photons that are produced in the hot inflow by different type of interactions in there. And baryons seems to be just about 1% of the initial content of the jet. The rest are electron-poston pairs. But more baryons might be injected by entrainment at different distances and also close to the disk, depending of the characteristic of the accretion flow, the level of turbulence, and so on. And at very long distances, matter might come from the interaction with different type of obstacles, such as broadline region clouds or stars that the jet can find in its path. So jets seem to start as Poynting flux, very relativistic jets, but very soon they get some matter from the annihilation of photons inside the jet and also from neutron decays. And then the jets propagate, and soon the jet will start to interact when it is dominated not by the field but by matter, with different type of things that the jet found in its path, and this will result in the heavy jets that we observe in some sources that produce huge impact in the intergalactic medium. Okay, I think that this is all. I apologize for not having the cursor. This made the talk very difficult. I hope that you have been able to understand what I have been trying to say. Thank you very much.
Thank you, Gustavo. This is the virtual applause. It was really clear, even though it was not, the cursor was not there. I don't know why, but it was really clear. Thank you. Thanks a lot. And well, we have some questions. First, Elizabeth.
Beth. Hi, Beth.
Oi, Gustavo. Tudo bem?
Tudo bem.
So, Gustavo, excellent talk and very interesting study. Really, very, very interesting. And but you still have the mass loading issue, right? So, and with this, hadrons, with this much less percentage of hadrons, if we have this shielding, magnetic shielding effect. Nevertheless, can I suggest an alternative solution to this problem? And it comes with the following reasoning. When you have the blend force IAG process, you develop this helical magnetic field. So the toroidal component is very strong. And because of this, the jet, the Poynting flux jet, becomes very unstable to plasma instabilities like current-driven kink instability. And the kink instability, once established, it breaks the lines very quickly because it distorts the magnetic column and breaks the lines. And this breaking, solves the problem of shielding, because then matter can get in. And also, on the other hand, because you have breaking of the lines, you have magnetic reconnection, fast reconnection, and therefore you can accelerate the particles as well. So in this sense, there might be some loading of hadrons as well, of protons, right? So would you comment on this, or do you believe that still we would have a larger percentage of injection of electron-positron pairs rather than hadron production in the case that we break this shielding?
Well, yes. What you are saying essentially is that, let's say, when we are in a situation like this one here, now I think you can see the cursor, right?
Exactly.
Yeah.
Mm-hmm.
So what you see, what you are saying is that we could have some instability here that produces turbulence and then magnetic reconnection here, and this can produce some level of mixing with the gas outside.
Yes, well, penetration actually, because you break the shielding. Actually.
Yes, that is a possibility, yes, but what I think is that possibility is even more interesting when you consider the necessity of reaccelerating the particles that are being injected in order to produce the radiation we observe. So it's not enough to inject the particles, but you need to reaccelerate the particles to a power law in order to observe the synchrotron radiation that we observe, and also the gamma radiation that we observe from the base of the jet. So in my opinion, the main role of this instabilities that you mentioned are related to the reacceleration of the particles and the redistribution of the energy of these particles in the right power law to produce the radiation we observe. I don't know what is the efficiency of this mechanism to produce some mixing or some injection of matter from outside to inside. But it's clear that this might be a mechanism for converting magnetic energy into energy of the particles that are already in the jet. And in that sense, I think that this is a very convenient in order to explain the observations, because you cannot invoke shocks because this is completely magnetic dominated scenario. So the plasma essentially is impossible to compress by mechanical effects. So you need magnetic reconnection in order to accelerate the particles. Regarding the entrainment by this mechanism, I don't know. I don't know whether there are simulations that study this problem or not, so I cannot quantify it. But what I clearly see is that this might be a very useful mechanism for the reacceleration of the particles. Perhaps you know some simulations about entrainment by this effect. I don't know.
Yeah, as a matter of fact, yeah, I can tell you that we have made 2 studies. In one of them, we did this study of relativistic Poynting flux dominated jets subject to the kink instability, and then we injected particles there, and they are efficiently accelerated by reconnection up to ultra high energy cosmic rays we do produce with this effect. It's a paper that is already in the Astro PH. We have just submitted this one that combines, actually, we do see that the particles are efficiently accelerated in these Poynting flux relativistic jets, you know, with the reconnection driven by the kink instability in these with initial helical fields. And in the case of accretion flows into black holes producing reconnection, we do see we have simulations where we do see this reconnection driven by magnetorotational instability. Again, you have turbulence, and then the lines get reconnected, so you have a real source of turbulent reconnection, and then you can accelerate the particles there already in these accretion flows. And we might expect, of course, we did not follow the entrainment of these particles into the channel of the relativistic jet, but we might expect to have this as well. But anyways, the idea here is that at the basis of the relativistic jet, of the Poynting flux dominated jet, because of the helical, it starts with this helical structure, and it's very easy to get unstable, to kink instability, and then you may have this break of the lines and break the shielding, and then you may have this penetration of material over there. But even though your study is very interesting, because you know this mass loading can contribute, just that I think that the mass loading, you may have also the hadronic contribution if you have this process of breaking of the lines, right? Breaking the shielding process. But it's interesting. We can discuss more this in private eventually.
Yes, it would be nice. I think that it's necessary to quantify this effect because, of course, these instabilities and the reconnection on the walls of the jet will introduce some particles, but also some particles from the jet that were injected by the mechanisms that I was discussing will be taken out. So
definitely, need to quantify, very important.
Yes, we need to quantify what is the net flux in the direction of the interior of the jet in order to know how much mass the jet will gain through this mechanism.
Exactly.
But quite interesting.
Yeah, we keep in touch, Gustavo.
Yeah, sure.
Okay, Reinaldo, you have a question?
So many thanks for the talk. It was very easy to follow, the explanation, very clear. I have it's a very simple question. In your conclusion that baryons account for 1% of the particles that you can put inside from the effects of, finally from the accretion disk, from the radiation from the accretion disk and neutrons and so on. So in your model, you used an assumption that the acceleration in the disk gives an injection with a power law -2. I'd like to know if, I don't know how well is certain this parameter, if the acceleration is a little bit less efficient, could it impact this conclusion of 1% or no?
Well, you mean the acceleration of the spectral,
disk.
or the spectral index, the efficiency of the acceleration, or the spectral index of the injection? Which parameter?
The spectral index of injection in the disk.
Yeah, well, that will change the number of particles that you will inject. So in the case of a harder spectrum, you will have more particles being injected in the disk, and in the case of a softer spectrum, you will have less number of particles being injected. But the changes are not very dramatically, because most of the particles that will be injected are produced very close to the jet in the innermost part of this disk. So it's not particularly sensitive to the spectral index. Of course, if you change from 2 to 3, there will be some effect that will be noticeable. But if you use 1.8, 2, or 2.2, the order of magnitude will not be changed.
Thank you.
We have explored.
But essentially, this
yes.
percentage between leptons and baryons would remain around a few percent, right?
Yes, that's correct. Yes.
Okay, Juan, would you like to ask your question?
Hi, yes. Can you hear me?
Yes, I hear you.
Thank you for the talk. Very nice talk. I'd like to, at the beginning of your talk, you commented on observational evidence for these blazars that exhibit an efficiency. If you compare the jet power with the accretion power, then this ratio is larger than 1, right? So my question is, what kind of blazars are more likely to exhibit this high efficiency?
Yeah, essentially those that present very powerful jets. So most blazars and also gamma ray bursts. So this type of magnetized, very strong jets are powered by spinning black holes in those extreme blazars and also in gamma ray bursts. If you move to, for instance, Cipher galaxies or other type of AGNs, then you don't need an extremely fast spinning, rotating black hole. So you can produce a moderate jet with a black hole with a spin that is not so high. And also, if the accretion of matter is close to the Eddington limit, then the efficiency of the outflow will decrease. So essentially what we are talking here about is jets of blazars, BL-like objects, flat spectrum quasars, or gamma ray burst. Other type of AGNs have less powerful jets, and then the efficiency of conversion of accretion power into jet power is of the order of 1 or less than 1.
Okay, thank you.
You're welcome.
Okay, we have a question from Pankaj. Would you like to ask your question?
Hi, can you hear me?
Yes.
Yes.
Yeah, thanks for a very lucid talk. So it's regarding the spectral energy distribution. So where you have the broadband spectrum, you showed that in the optical to probably, okay, infrared and optical, it's the thermal spectrum is dominating.
Yeah, you mean?
Correctly, yeah. Yeah. So is it possible other way around that the thermal spectrum is not there and you have everything non-thermal?
Well, yeah, I understand your question. Well, it depends on the accretion rate. If you have a low accretion rate and you have some of these RIAF or ADAF or these coronas around the black hole, then these plasmas will cool essentially because of the temperature they have through inverse Compton upscattering. And since the tail of the Maxwellian distribution of the plasma necessary will be relativistic, you will have synchrotron radiation. So for instance, for the parameters of, let's say, an object such as M87, you really expect some thermal synchrotron radiation. This is probably the kind of radiation that was observed last year with the Event Horizon Telescope around the supermassive black hole in M87. Now, some people suggest for not for extragalactic sources, but for galactic sources, that most of this radiation might come from the jet, actually, see? The problem is that there are so many open parameters in this model that it's very difficult to differentiate from the base of the jet from this hot outflows. But in that case, you will have problems with how you are producing a jet with so many particles and with the power of the jet. So I'm quite skeptical about these models that suggest that everything comes from the jet and everything is non-thermal. I think I feel very much comfortable with this type of models because they do not have problems with the launching of the jet as the other models.
Okay, so just a related question. So like, let's say, okay, at least in the kind of, I mean, in the blazars, we say that, okay, it's the jet that dominates, at least it's outside. But okay, as you talk about the M87, it's a nearby galaxy and it probably, I mean, okay, it's not aligned with our line of sight. So because if it is not due to jet, don't we expect to see these things quite often in those sources compared to the blazars where it is relativistically boosted and outshined?
In the case of M87, there is some modeling, especially now with this data from the Event Horizon Telescope, that they invoke this kind of thermal Comptonization and also the thermal synchrotron radiation. Some papers that appeared last year and even this year, if I remember correctly. So I think that there is no strong reason, even in the case of M87, to think that the spectrum from the innermost part of the source comes entirely from the jet. So the jet dominates at scales of several gravitational radii, as I show you in this image. That this is from M87, this one. So of course, synchrotron radiation from the jet. That there is no question about that. But all this spectrum, all this radiation that you see here, is contained just in this point here. So only with the Event Horizon Telescope you can study what is going exactly here, and what you observe there is something more like this, where the emission seems to come from the hot inflow and not from the jet that at these scales is completely magnetized and is shielded, and we have all these problems. So this synchrotron radiation is produced beyond a few gravitational or Schwarzschild radii from the black hole. But if you look directly at the black hole, this part here, most of the radiation will come from the disk, not from the jet.
Okay.
Okay, so we can finish the transmission with this, and we can stay a little bit in the Google Meet to discuss a little further if we want. But Richard, very good.